This talk is going to be about my personal journey from like configuration management to what we call GIFEE, Google's infrastructure for everyone else. I'm going to kind of keep this high level. We are a little bit ahead of time, but I'm going to try to keep this short so we can get out of here. But the idea here is that a lot of people saw this magical command ran by Brendan in his Kubernetes talk. And a lot of people were like, wow, that was a lot of things that just happened with a single command. How do you actually get a system set up that can actually do that, right? How do you go, what's happening a little bit behind the scenes? So we'll get to that. So one question that I ask a lot of people, like, why are you here? What's the purpose of adopting all of these technologies? Why do you actually deal with servers? Some of you are only here for the cookies. Some of you don't even have servers. But you know, the ones that do have servers, it was very consistent that people are actually trying to build products that add value and you get paid, right? So if those first two things work, you should be getting paid. And if they work out well, you rinse and repeat and you keep building more products. What I didn't hear from people is that they really were anxious about managing user accounts, RPMs, and attending change management meetings, right? But the reality is that's what many of us are actually doing with most of our time, right? If you really look at how much time you spend actually building and solving problems, you actually spend way too much time managing those things that are really not important. That's not what you signed up for. And then once you actually are tasked with those particular set of problems, you're always like, hey, we want you to do all that stuff and keep it available, right? And you don't necessarily have the time nor the tooling to do this. So people come with this high availability thing, and they're like, hey, we want 5 nines, right? And I ask a lot of people, like, how much downtime can you have for 5 nines? Does anyone know what the answer is? In 1 year, how much downtime can you have? About 5 minutes, right? So what do? We go out and we order a bunch of these, and we give them to our sysadmins, and we make them highly available, right? So you get that first call, and you wake up, you look at the pager, you run in, you solve the problem. You do it in like 3 minutes, right? Woohoo! You're still in SLA, right? You can claim 5 nines for January. And you have 2 minutes for the rest of the year. I got news for you, you're going to miss your SLA. And one way that most people attempted to solve this problem was with configuration management. So a lot of people, when they entered the industry, you saw a lot of the things that Brad was doing, where you have like this build script. Like, here's how you deploy the app. If you follow set steps in the right direction, everything will work out fine for you. And then we wrote a bunch of bash scripts, and we were like really proud about those bash scripts. And then we evolved, and we encapsulated those bash scripts into configuration management tools. So I used to work at Puppet Labs. I have no bash against any of these configuration management tools. But at the end of the day, if you look underneath the covers, most of the configuration management tools are shell script compilers, right? You write in a high-level language, sometimes YAML or dialect of Ruby. And at the end of the day, it compiles all that into a manifest, a bash script that's going to run in a certain order, and it tosses it on the other side of the machine, right? And then what we end up with is, if I were to show this, so like one of my preferred configuration management systems is Ansible. How many people have used Ansible before? Awesome, that's a nice set of you guys. So one good thing I was very surprised about is that Ansible actually runs on CoreOS. So someone's done the work of using a statically linked PyPy Python implementation. So we can actually use Ansible on CoreOS without doing anything weird. So what I normally do to get things set up on CoreOS with Ansible, I usually run this playbook. So before my talk, I got it all set up to make sure that we have all the bits we need to use Ansible, right? So let's say you want to deploy an application with configuration management. And here's the important point where I think tools like this have some scaling issues, and mainly in terms of the way you think about things. So normally with configuration management tools, if you want to deploy a service, in the case of Ansible, we can write this hello service playbook. So what we need to be concerned with here is, in this case, I'm going to deploy a static go hello binary. I'm going to ensure that there's a systemd unit file in place. And at the very end, I'm just going to make sure that that service is started, right? This is a very common pattern. Some people are very familiar with this idea of a file package service. This is like the holy grail of configuration management. If you can get to those 3 steps to deploy your app, you're doing pretty good. But the first thing you need to do with most configuration management systems, even if you run them in like masterless mode or just from your laptop like I'm doing here, you need some form of an inventory. So what I need to know is, like, what are my target hosts? And I have to give them identity, right? You can use fancy host names, or you can use IP addresses. In the case of Ansible, we have an inventory file that we have by default. So I have a category of machines that are like CoreOS machines, so I can bootstrap them, and that's what I did with the site.yaml. And then I have a group of machines that I'm going to give a role of hello, right? So those two machines, .100 and .101, they get to run the hello application. We saw what those steps are. So what we can do is have Ansible run that. So we'll take that hello playbook, and now that we have those machines, we get to target both of those machines. And Ansible does some fanciness and does it in parallel. So now we have Ansible that just deployed the set of services to the machines. Right? But we're very node-focused here. Right? So if we wanted to add a new machine to the cluster, what do you got to do? You go back to this, this process, and you add another machine. Let's look at this machine. So we'll grow our cluster, right? So we added a new machine to the cluster, and what do? We run Ansible again. And now we have 3 hosts in our setup. So I ran this before, so it's all green, that those things are actually up and running on our system. And for most people, this is a really good place to be. Like if you're here and this solves your problem, you should applaud because that is a lot of work to do this level of automation. And for some people, they're just not even here yet, right? They still have those bash scripts that are, you name them after dates, like bash February 15th. And that's the one you run now. You laugh, you got that like secret stash of bash scripts? No, don't run that one. There's one newer than that, right? So Ansible kind of moves you forward. But when I was reviewing some of these things, right, you go out and you automate all this stuff. And then someone asked they asked this question like, hey, I want 3 of these things on each host. Now, if you used RPMs or apt-get before, that is not an easy thing to do, right? Because most RPMs have a name, and you can only have one of those installed on the system at the same time. And this is actually not a trivial thing to solve. And when you look at some people's systems, they have all this symlink magic going on. They just say, let's just bail from all of this and just have this git pull, and we'll symlink them and give them different versions and do some magic. And what that actually looks like is people will build service files that look like this, right? So this is the scale-out version. We're going to scale the hello service. And what you end up doing, this is supposed to be a declarative system here. This is YAML. And they turn YAML into like this pseudo language where you can actually do like these little for loops, right? Like with this number, we can deploy n number of these hello apps, right? So we're going to name them each different based on a sequence number. And what we're going to do is we're going to have a bunch of systemd unit files. We're going to have one called 1, 2, and 3. And luckily for us, our app, we can kind of give it a port by using the -p flag, and we can have each of the apps bind to a separate port. Right? So this is how we're going to overcome the limitations of our system. We're going to bail out to some for loops. And in order to do this, we need to update, guess what, our inventory file again. So we have this inventory file, and we need to give them some variables. So we have all 3 of these machines. And what we need now is to say, the developers say, look, we want 9 of these apps running in the cluster. So I talked to a lot of the configuration management people, if you're there. I asked them, like, do you have a scheduler? And they say, no, I do not have an automated scheduler. I'm like, you're the scheduler, right? Like, the sysadmin team is normally the ones doing the scheduling. So now I'm going to basically do a static scheduling of all of these particular instances. And the way that works is, given that criteria, I need to set some variables. So the variable I need to set up is the instant count. So I'm a really intelligent scheduler. Right? I'm going to fairly balance this load across all the machines. So what I'll do is edit this host inventory file, and I'll set this variable. And I'll say that each instance, we want it 9, so we'll just give each of them 3. All right, so now we have our intent, and we will go ahead and schedule this. So we'll run now the Ansible playbook for the scale-out service. And what should happen is we should get 3 instances of this binary on every machine. And we're starting to see this now, right? Our count was low. Ansible detected that. And now we've kind of scaled the service, right? So in each of these machines, if we take one of these machines and we look at one of the ports from the systemd unit files, we should be able to hit that. So let's go to our browser, open a window. Let's see if this is actually working. 50. Oh, yeah, so we have hello world there. So our app is actually deployed. But here's the limitation on this system. Let's say people say, now we want 6 of those instances. So what do? It's very obvious. You go back to the inventory file. So we go back to the inventory file, and we want to express our desired state. Right? Simple enough. What do you guys think will happen here? Will Ansible break? Will it do the right thing? What do you guys expect it to do? Right, so what will happen is this thing will run and say, yes, there are 2 instances on every machine. That's not really what you meant. You meant no longer 9, and now I want 6. Ansible doesn't know anything about that. So that last instance is running on all the machines. And even though you check in these configs, it actually doesn't represent the cluster state. It represents the last set of actions you ran. And it's not really clear what your intentions were, right? So how do you figure this out? You log into the box, you have all these monitoring tools to figure out there's too many things running, you may kill them out of band, and then people start to distrust this system because the system is actually not enforcing any state here. It's just the last thing that you ran. This is very, very similar to running bash scripts, right? You run a script and the last thing that happens wins. Now these systems are a little bit more sophisticated, but you're kind of left hanging here. You can't look at the configuration and say that's what's actually running in the cluster. Doesn't mismatch. And the reason for this mismatch is because the application is tied to the host, and also that we don't have anything that's really aware of the full cluster state. So how do we fix this? So the question we need to ask is, like, what happens if we decouple the application from the machine? What if we're able to talk about the machine in complete isolation than the underlying servers that are running those machines, right? So this is where you start to have the separation of responsibilities. Now, there's people that rack the servers. There's people that get them ready to run some, in our case, we want to move to maybe a cluster management system. And what we want to do is have that be a separate set of concerns than the people that move that dial between 9 and 6. So I got introduced to this new way of doing things, like most people, through Docker, right? You heard about containers, but they really weren't practical to use, mainly because the workflow was missing. It really wasn't obvious what to do next. And when Docker came out for a lot of people, its API kind of gave you a hint on what you wanted to do, right? You wanted to run some things on a system, and when you tried it for the first time, it was like magic, because you could actually run 5 different instances on the same server without doing all of those tricks that we saw there. And after my search after learning more about Docker, the first thing I wanted to do was find a host that actually had a newer version of Docker. That was my #1 thing, and had actually a new enough kernel to actually use all the Docker features. And I ran into CoreOS. And CoreOS does a lot of things that's pretty nice. So like, if you're managing systems and you're using configuration management tools, the one thing you got to do initially is strip the system way down, right? Take off all the things you don't need and kind of get a base system that you think is secure or is a good starting point for the rest of your infrastructure. And CoreOS, for me, does that out of the box. And once you have CoreOS, now we could use the Docker API directly, but we're still talking about hosts, right? Like, you have this remote API, and you can build a bunch of tooling around that, but you're still kind of in this mode where the host is that important. And then last year sometime, and when I say CoreOS, I'm talking about like things like Fleet, Rocket, Flannel, the whole suite of tools. So even though CoreOS is our name and also the same name as our operating system, it represents all those projects on GitHub that allow us to solve some of these problems. And what I want to do now, and one of the things that we talk a lot about at CoreOS is like distributed computing. And for a lot of people that don't have those PhDs, myself included, when I think about distributed computing, I want to take a collection of those systems and make them act as a single system. And this is when things get really, really hard. And this is when we need things like etcd to provide consensus on the network. And this is when we have to start building tooling that allow people to treat a cluster of machines like a single machine. Then things get simple for the users. The system is more complex. I won't lie. If you're using configuration management, these systems are way more complex than Ansible or Puppet. A lot of times you hear hand waving that, oh, it'll be simple. It's not simple. It's way more complex. But if you know that going in, we'll see what the benefits are if we are willing to embrace that complexity. And then a system like Kubernetes comes along, and it's right in line with our way of thinking, my personal way of thinking about these things. How can I treat this collection of machines like a single system and start talking about deploying applications and not necessarily dealing with specific hosts? Now, one thing we can do with Kubernetes is we've got to deploy it. So a lot of the demos, we went straight to the action, like, hey, here, use this API. It's awesome. And one of the goals of this talk is how can we reduce the magic of this one command? Like, how do you get to be able to run a command like that? Well, the first thing we need to do is we need to build up the system. So right now, I use Fleet, which is part of the CoreOS stack, as my machine database. So I can say Fleet, list all the machines on the system or in my cluster. One PSA you see here, the etcd machine is not in this list. I've met a lot of you today, and it was awesome for a lot of you to come up and say, hey, you helped me on IRC. That was awesome. You really care. But the thing is, most of you are coming to IRC mainly because you're running etcd on the same machines as your workload. etcd starts starving and can't do heartbeats, no CPU, and your cluster's down. All the way around, your cluster's down. So what I'm doing here is I'm making sure that etcd is isolated and it doesn't show up in the Fleet list. So once I have a group of machines, I can use Fleet to do some scheduling for me, right? So instead of assigning these machines roles and profiles, I can give them metadata to help influence the scheduler. But the only thing I'm doing here is just I have a helper tool that will look at this metadata and automatically register nodes with the Kubernetes API. But before we get there, we need a few bits. The first thing that we need, so recently over the last couple of days, we announced support for Rocket can be ran by Kubernetes, and it also supports Docker. Realistically, a lot of people will probably get started with Docker because they have a lot of content. But in the coming weeks, you'll start to see a lot more tutorials around Rocket being supported in Kubernetes and deploying things that way. So let's start with that. Oh, and another thing, cross-host networking for your containers. A lot of the talk today talked about optimizing the network by giving every container a first-class IP. So how do you set that up? Well, at CoreOS, we built a tool called Flannel. If some of you guys were in the breakout session, you saw an overview of what Flannel is. And the way you would install Flannel, in our case, is with Fleet. So Fleet is our distributed init systems, distributed cluster-aware init system. So what I can do is say Fleet start Flannel. And this is going to trigger a global unit. I actually need Flannel running on every single machine, right? But not etcd. So if we look at that unit really quick, we'll see that down here at the very bottom, we see that we have some requirements here. We want this to run on every machine in the cluster that has this metadata called role equals Kubernetes. So at this point, all the machines in the cluster should now be running Flannel. And what Flannel will do, and the way I like to describe Flannel, is like DHCP or for your L3 subnets, right? So you have a larger subnet, and what we do for efficiency, we carve up a large subnet into smaller subnets that we give to every host, and we manipulate some route somewhere. So now we have our base system set up for doing cross-host networking, and now we can get into containers. One container runtime people use, and I'm going to start Docker, since a lot of people are familiar with that. We'll start the Docker service. Again, a global unit. I want Docker running on every single machine. So at this point, Docker is now integrated with Flannel. And we can check that by asking Fleet to list all our unit files. So at this point, we have Docker running on every machine. We have Flannel running on every machine. So now it's time to move on to getting Kubernetes set up. So how do you get Kubernetes set up? Again, we can use Fleet to deploy a more advanced scheduler. So what we'll do is we'll start with etcd. So Kubernetes, we like to just give it its own etcd service. You can actually reuse the one that you currently have. There's no reason you need to do this, but I'm going to go ahead and do that. So we'll start etcd. So what will happen here, I'm actually influencing the scheduler to make a decision for me. I'm telling etcd to go to a specific machine. So I can use some Fleet metadata and say, etcd, I want you to land on a machine that has this machine ID. And mainly because this is a stateful service, so I want to make sure that it stays there. The next thing we need to do is spin up the Kubernetes API server, right? So I'll just spin up the kube API server. And what I want right now is I want that thing to go wherever etcd goes. So I just have a dependency on wherever the etcd service is running, you need to run there too. So the API server is the thing that we talk to. This is the thing we issue commands to. This will give us that illusion of a single machine. It will be the entry point for everyone to participate and activate with the cluster. The next thing we need is a controller manager. The controller manager is the thing that will allow us to go from 9 instances to 6 or 6 to 9. This would be like our autoscaler. This will be that intelligent thing that kind of enforces our state that we actually want. The next thing that we need in a Kubernetes cluster is a scheduler. And a scheduler is the thing that tries to make the decision on maybe if I have multiple pods that need to run, maybe they should live on different systems. There's other scheduling algorithms like bin packing, fill up one server before you move on to the next one. So we need that scheduler running. Now, the scheduler is going to follow the API server because I gave it the same constraint. And what we need to do now is we'll have Fleet start the rest of the components. So now that we have this collection of servers that make up the Kubernetes API and its supporting services, at this point, we need to prep all of our workers to be able to receive work. So how do we do this? Well, there's a unit or a binary called the kubelet, and it's the thing that interacts with the container runtime. This could be Docker, and this can also now support Rocket. So what we'll do is we'll ask Fleet to start the kubelet on every machine. And the kubelet is what the scheduler gives work to, and its job is to interact with the container runtime and keep the things that it's responsible for running. And then finally, there's a proxy server. So a lot of those rolling, automatically upgrading things that we're able to do, the reason why we're able to do them is that we have a service proxy running on every machine in the cluster. So if we have 100 machines in our cluster, but we have the actual containers only running on 3 machines in that cluster, what the service proxy allows you to do is hit any machine in the cluster and be proxied to wherever the pod is actively running. That means if you kill those 3 machines that were running your pods, Kubernetes will reschedule them to another set of machines, and you can still hit any of those machines and find out where they land automatically. And this is by doing label queries, and the proxy kind of abstracts that for us. So we'll start that service. So at this point, we have the entire Kubernetes stack up and running. So we have a bunch of units, and the nice thing about doing it this way, and this is kind of the secret sauce in Tectonic as well, we use Fleet to do this. Not all of the secret sauce, but some of it. And what we get from this is that we can keep all of these things up and running. At this point, we've declared that there's a bunch of global units that need to be running on every single machine in the cluster. And we start racking new machines into this particular cluster. They're automatically going to get Docker. They're automatically going to get the proxy server. They're going to automatically get Flannel. And then we can continue to grow the cluster. Our intent is encapsulated into the tool. So at this point, we can start using the Kubernetes API. So I ran the command, there's no nodes in there. The nice thing about Fleet, it has an API, so we can interact with it, and we can register those machines with Kubernetes. So we'll just start that really quick. So Fleet, start, units, the kube register service. And another nice feature about Fleet is we can still go get those logs. So one of the things that we like people to do is like, how can we build good tooling that prevent people from having to log onto the server? And one of those features in Fleet that allow us to do this, we can actually use the journal to see what's happening with this service we just launched. Right? So those are the logs from the machine wherever it landed, and I can kind of see what it's doing. And it registered the 4 Kubernetes machines with the Kubernetes API server. And at this point, we see that our nodes are there. Right? And now we're getting towards the end, and we're leading right back up to that magical command where we can do this rolling update. Right? So the first thing we need to do in this particular thing I'm going to do is going to deploy some pods. And the pods are the execution unit that we have in Kubernetes. Now, I'm not going to go too deep into what a pod is, but we'll look at a few. And one that I'm going to use is our Postgres. We have a database in this particular application. So we'll have some pods. And I want you to just look at how they're defined. We're not going to go into detail here. But basically, we have a schema that defines what our pod needs to be, labels so we can attach services to them, so we can dynamically find this pod once it's scheduled. And towards the bottom, remember, I talked about earlier that containers do not make things magical. If you have a stateless application, it's probably going to have state that lives on the server. But in Kubernetes, you can define that you have that requirement and bind mount in any data volumes that you need. This is just the reality of a lot of services that we have. And don't feel bad if you're in this situation. There's tools to make it happen, and Kubernetes is willing to meet you where you are. So we'll start this really quick. So we'll do kubectl, and we'll basically create our Postgres pod. So now it's up and running, and what's actually happening behind the scenes, that pod is being scheduled to a machine, 100. And now that it's up and running, let's see where we are. It's pending. So what's happening is it's pulling from its container registry, and now it's up and running. Now, we could hit this pod directly, but that's not what we want to do. We want to give it a service IP. So let's create one really quick. So kubectl will create a service for Postgres. So now we have the service IP, and this was some of the magic that we saw in the service proxy. So what we can do now is kubectl, get all the services on the system. So at this point, we have a magical IP that we can use to reference that particular pod. And if this is all working, -h, and then what we should be able to do is log into this particular service. So it's working, right? So Kubernetes is doing this thing. I'm not concerning myself with what host it's running on. I'm able to interact with it with this service IP. Now, as we get closer to the end of this demo, I want you guys to pay attention to something. One thing that Kubernetes specifies is with that service IP, it injects those service IPs as a set of environment variables into every app that should see them. Right? So in Kubernetes, there's this concept of namespaces. What I'm doing now is just deploying everything in the same namespace. So you can imagine your network team creating that service for you, and it's going to allocate a VIP. But you don't need to concern yourself with that in your app. Just reference this environment variable. There's other ways of doing it, mainly like through DNS and other mechanisms. But this makes it really easy to kind of connect two services together. So this app that we're looking at now is called PGView, and its job is to interact with the database. And we'll march to the tail end here, and our goal is to deploy. I'm going to start with one instance of an application. And what we want to do is we're going to deploy another pod, actually a replication controller. We want something that will allow us to scale it up and down. So we're going to use a replication controller for that instead of a static pod. So what we're going to do is create, let's get out of this. We're not going to do it inside of Postgres. It'd be awesome if it had that feature. All right, so we're going to create a replication controller. And this is very analogous to like an auto-scaling group in Amazon. So we have this replication controller. We're going to install PGView, the stable v1 of this. So what we want here is a replication controller to keep an eye on things. We have a specification. Right now, I'm saying I only want one of them. And what we'll do is we'll use kubectl to get the set of pods. So we have one running per our definition. And what we can do is see if this works. So this pod is unique. It runs my application and memcache. Thank you, Brad. And with memcache, I can do things like local caching per pod. So this is the way you express I need multiple containers to be scheduled together as a single unit. This is really awesome if you ever tried to do this with like a package management system. You can actually express this in Kubernetes. So in this case, we're deploying memcache and my app together. So it's up and running on the machine. And I'm also going to give it a service IP. One thing you need to pay attention to, and so how some of this magic works, are these labels. Most objects in the system understand how to find things based on labels. We're going to deploy a service proxy or a service for this particular app. Let's do that really quick. And where we're at now, we'll do one for PGView. All right, so now we have a service in place for that, and we should have a service IP. So this is what you give out for people that want to interact with the service. All right, so we'll get our services. So now we have our services. We can grab the one for PGView here, and let's just see if it's working. And we can use curl to hit this RPC service. All right, let me just type it out. Curl this thing. And it's an RPC service, so we run this command. Let's do version. All right, so we have 1.0 of the service running. And what this thing actually does, it just talks to Postgres and says, hey, what SQL features do you support? And spits it back as a big blob. I introduced a slow sleep in here to say, hey, here's a penalty for making a SQL query. You better cache it next time if you want it to be fast. So memcache is actually working in our pod. But what we'll do is we'll just see what the customer sees. So let's just say you're launching your service, and we'll just leave it running. So while true, do this thing, and then we'll sleep in between so we can kind of follow the progress here. And we'll dive a little bit deeper into what Brendan was doing. So what we're having here is we have the RPC running, and then we'll sleep for 1 second, and then we'll be done. All right, good. All right, so now we're getting very close to what this command was doing. So what we want to do now, we like our service. We'll just resize it. Resize. And then we give it our set of replicas. And now we want to go from 1 to 3. And we want to do it for PGView stable v1. So that's it. We don't really need to concern ourselves with what servers will run it. We just know that the cluster is going to try to enforce our state. So if this works, we'll get our pods, and we see that we now have 3. And I'm not concerning myself with host names here. I just asked the cluster to give me more of those instances. And now they're up and running. And now they're up and running. Here's what our end users see. So we're still at 1.0, but we have a little bit more scale here. And now we get back to our command, right? So this is what we ran. And now that we're using Kubernetes, we're pretty much set up to do this. So we can say kubectl, I want to do a rolling update to the new version of this thing. So I want to do a rolling update with an update period of 2 seconds. And we want to update the pgview stable v1. And we're going to create a new replication controller that has our new specification. Mainly a new image version is what we're looking for here. And here's where Brendan left off yesterday. And so now we have this orchestration of the Kubernetes APIs to migrate us from one version of the app to the other. And what are our customers seeing, or users seeing here? Eventually, what should happen if our service proxy is working and all those images get pulled over, we should start seeing 2.0 refresh throughout the cluster. And there's our first instance of it. And every 2 seconds, it will do the whole song and dance until we have all of them migrated over. So the majority of the cluster is doing it. We're getting close here. Hopefully the next iteration will be done. Stubborn. Oh, they're just trolling me now. 1.0. There we go. We're 2.0 across the board. And with that, that's the end of the demo. And hopefully you demystified how this actually works in real life. Thank you.